Welcome back to the Punny Math Teacher. Today's expectations are to remember that you're using twice this video's length. So I'm going to try to keep each video between 10 and 15 minutes. And that way you can spend 20 to 30 minutes making sure you process this, pause, take your time to write, make sure you're adding more annotations to the notes, making sure you and your future self remember what you learned and why it all works. So for this unit, remember, we are putting all the unit objectives together. We've already named our polynomials, we've added, subtracted, we've also multiplied them, and we've graphed them, and we've solved by graphing. So now we are on simplifying radicals, and we're going to get into square roots, which is another name for the radical, or the common radical, and just looking at operations with those, and that will actually lead us into the square root property and our last set of notes, which will be the quadratic formula. So these are the basis for a lot more, for many more notes. All right. So there's our comprehension. So this is the back side of our table of contents again. So we've already done 40 through 45. We are now on pages 46 and 47. So in this one video, hopefully we can get through both pages. Just a random FYI. So the first page is going to have a box of 4 different examples, and then the next page will also have 4 examples. Example 1A, 1B, 2A, 2B. I just didn't draw the boxes around them, but you're welcome to if you'd like. So just an FYI, and that's what our organization will look like. So without further ado, let's go to page 46. Okay, so simplifying radicals, we are going to do actually 3 examples. The first box is just for definitions and vocab. So make 4 boxes on your whole page. We're going to have an example 1, example 2, and example 3. So if you want to label those already, you're welcome to. So we're going to start with, what is the square root of 25? So the square root of 25 is 5, and this is because 5 multiplied by 5 equals 25. All right, and we're going to stick with the basics that we're assuming that it is a positive. I might make an extra random video of why there's positive and the negative and that symbol thing, but we're going to just focus on the basics for this lesson, unless I have time at the end. So square is a number multiplied by itself. So 5 squared is 5 multiplied by 5, which is 25. So 5 squared makes 25, and thus the square root of 25 would be 5. So they're inverse operations from each other. If I square something, I'll end up with a square, but if I square root that square, I end up with the original number, which was 5. All right, so then putting that in a definition form, a square root is going to be what number multiplied by itself gets the given number. So we can actually, if we want to see it this way, so the square root of 25 can be rewritten as the square root of 5 squared. But when you square a square root, or square root a square, because the order doesn't matter, as long as you do both of the same argument, that's going to leave you with that argument. So if you have some value, some number squared, then you take the square root of it, you're going to end up with x. This could also be written, you're not going to see it very well, I guess you might see it, is if we'd had the square root of x squared, that would also give us the argument x. So both of these, it doesn't matter if you take the square root first and then square, or square first and then square root. Both of them will be inverses of each other and undo each other and end up with the argument of just plain old x. Where was I going with that? Oh, so the radical sign is just a little check mark thing with the bar. The 2 is called the index. So square root is the typical radical. If you don't see an index, assume it is 2. All right. There are such things as cube roots. So if I wanted the cube root of 216, I'm asking what times what times what. All of those are the same number. equals 216. In this case, it is 6 times 6 times 6 to get you to 216. That would be the cube root of 216. So if you see an index that's not 2, then that's the index. But if you see 2 or just no index, then assume that it is 2. All right, so example 1, we're going to simplify radicals. So this is a radical because it has the radical sign. There is no index, so I'm assuming it is 2. And we can actually rewrite radicals like we did over here by breaking them down into their factors. So it's really nice if we do a factor tree. So our first step to simplify large radicals will be using a factor tree. So I'm just going to write the 180. What multiplies to make 180? Well, since it ends in a 0, I know it's going to be 18 and 10, but you could have picked 90 and 2. That would work too. All right, 18 would be 3 and 6, 6 is 3 and 2, 10 is 5 and 2. And notice in this factor tree, I'm going to circle all the ends of my branches. These are all prime numbers. I can't break them down any farther besides this number and 1. By breaking down 1 bajillion times, 1's not prime or composite because 1 can't be multiplied by another number than itself because 1 times 1, that is the same number. So 1 is neither prime nor composite. 180 is composite because there are multiple factors that make it up. But a prime number only has itself as its own factor besides 1. So these are my factor trees. Those are my primes. So I can rewrite 180 as 2 squared because there are 2 2's as its prime factors. There are 2 3's. And there is 1 5. If there is no exponent, then it is assumed to be a 1. You're welcome to draw that 1 if it helps you, but you don't need to. All right, and that means I can rewrite it. So I'm going to rewrite the square root of 180 as the square root of 2 squared, 3 squared, times 5 to the first. Now, square roots are 2 numbers that multiply by themselves. So that's 1 number multiplied by itself, so it makes 2 versions of that 1 number. That is a square root. So because there are 2 5's being multiplied here, I can pull them out and it just ends up with 1 5 because the square root of 5 squared is 5. So the square root of 2 squared is 2. The square root of 3 squared is 3. The square root of 5, oh wait, that's not squared. So that actually has to stay inside of my radical because it doesn't have another pair to then find the inverse. It's not being squared, so I can't do the inverse operation of this square root. And then I simplify this and I get 6 square roots of 5 as my final answer. So this is simplifying the 180 square rooted because I went from 180 in my argument down to 5 in my radicand. So I have 6 square roots of 5, that's the same as the square root of 180, but now I can do more things with it because it is simplified and squished down. So let's try another one. Square root of 27, if you want to pause and try it on your own. So I'm going to do a factor tree from here. So you could do it from here. When you do, technically you should be putting square roots on them because square root of 3 times the square root of 9 makes the square root of 27. And if you're here and you know that square root of 9, hey, that's a perfect square. The square root of 9 is 3. Then that one's going to give me 3. That's a loner. And so my answer will be 3 square roots of 3. You could also follow the process from above. If you did that, you'd end up with 27, 3, 9, 3, 3. Those two are squared. There's a loner 3. So I'm going to get the square root of 3 cubed, which is the same thing as saying the square root of 3 times 3 squared. So I have a 3 and a square root of 3. Both of those would work, okay? Both ways get you to the same answer. But recognizing your perfect squares will help speed up your process a lot. So I would definitely make sure you know your perfect squares 1 through 20. 1 through 12 would be great, but 1 through 15 is even better. As high as you can get there. I mean, 17, 18, and 19, I really don't know right off the bat. I probably could recognize them, but I have 1 through 16, because 16 is 256, and then 20 is 400. So I have 1 through 16 solid, and then I have 20 randomly. Okay, and then 3, what if we had a coefficient already, and then we had the radical? So I'm going to leave that 5 alone until the last step. I'm going to ignore it until the last step. So when I do this factor tree, 384 ends in a 4, so I know it's even. So I know 2 goes into it. Half of 300 is 150. half of 80 is 40, half of 4 is 2. So 150 plus 40 is 190, plus 2 is 192. 192 also ends in a 2, so that's 50, 95, 96. I think, let's see, 3 goes into this, because 9 plus 6 is 15. That's a multiple of 3, so I'm trying to get bigger numbers, and hopefully that I can get, so that's 32, so that's 8 and 4, that's 4 and 2, that's 2 and 2, and that's 2 and 2. And then make sure you hit all of these branches. So all the prime numbers you have to circle to make sure you found them all. If I had thought about it, I could have gotten this with 32, and I could have done 16 and 2, and that 16 already would have known its square root, but that's okay. So this is 5 square roots of 1, 2, 3, 4, 5, 6, 7 2s, and 1 3. Okay, so if it helps, put the little dots for multiplication. So I have 7 2s. I'm going to use a pen. So this pair can come out. So I have to keep the 5, keep the 2. This pair can come out. This pair can come out. But then I'm stuck with this loner and this loner. And that means I'm stuck with a 2 and a 3 inside. Okay, and now this is my last step, so making sure that I always have that 5 out in the front to multiply by. So 5 times 2 is 10, times 2 is 20, times 2 is 40. So it's 40 square roots of 6. That's my final solution or simplification for my radical. Now, our next page is going to be radical operations, so this video is probably going to get closer to 15 minutes. I'm going to try to rush it. Remember, you can always pause, okay? I'm trying to hit 15 minutes just so that you have time to pause. If I go too long and put too much wait time in, then it gives you less time to do anything with. Okay, so example 1A and example 1B. So these examples are going to deal with multiplication. The next 2 examples, example 2A and 2B, will be on division. So for this one, again, it's 3 square roots of 16. You could do your factor tree and do it just like we did on example 3 from the last set of notes on last page, on page 46, or realize that this is a special case, as a perfect square. That's what it's called, perfect square. So this is just 3 times 4 equals 12, and you're done. So if you know your perfect squares, life goes so much faster. Okay, example B, what if I had the square root of 3 multiplied by a square root of 18? These are different radicals, which if they were the same base, same argument, I could add them, but I'm not adding them, I'm multiplying. So this is actually the same as doing the square root of 3 times 18. So I could do the square root of 30 plus 24 is 54, and then break it down from there, which if I have my factor tree, then I'd end up with, this is the square root of 9 times 6, so it's 3 square roots of 6. You could do it that way, or if I wanted to, I could break down this 18 first and then make it a simpler process. So 18 I know is going to have a 9 and a 2. 9 is a perfect square. And so this would be square root of 3 times the square root of 9 times 2, which is the square root of 3, which is the second method, times 3 square root of 2. And then I can have, there's an invisible 1 in the front here as a factor, as a coefficient. So 1 times 3 gets me 3, 3 times 2 gets me 6. Okay, I want to pause here so that I can discuss both of these methods. So the first method, I just multiplied both arguments. 3 and 18, stuck them together, saw what I got 54. I did the factor tree. Now, the factor 54 is a common multiple. It's a common multiplication fact. You should know what are 2 common numbers that multiply to make 54. If you don't, feel free to do a factor tree and then do the method from before on page 46. Totally fine. So I know 9 and 6. Square root of 9 gives me a 3 without the radical sign because 3 squared equals 9. So the square root of 9 gets me 3 because they're inverse operations going back and forth between each other. And that 6 has a 3 and a 2. Those aren't squares of any sorts, so it's going to be stuck inside the radical sign. That's why this method stuck at 3 root 6. This one, I wanted to simplify this 18 as much as I could first and just get smaller numbers in general, which worked because I have a square root of 3, that's the same, and now I have 3 square roots of 2. Well, 2 is way smaller than 18, and so now I can just do 3 times 2, gets me the 6 stuck inside, and then 1 times 3 gets me the 3 as the coefficient on the outside. So it's up to you which method you prefer. It also is up to whichever example you're working with, and if it's a small enough number that this makes sense, or maybe a small enough number this way makes sense. It's up to you if it's too large and you want to try something different. There's more than one way to do stuff, which is awesome. Okay, this one. Square root of 35 over 15. So we can again split this up. So yeah, so we could actually split this up and get the square root of 35 over the square root of 15. This is one method. Okay, I am going to draw a line down here. This is one method, but sometimes this method isn't very helpful because what factors are in 35? 7 and 5. Both are prime and none of them were squared. 15? 3 and 5. Both are prime, none are squared. So this actually means that we are stuck. That was a weird arrow. But we are stuck. So we're going to have to try the other method. And the other method is simplifying it first while it's all in one fraction. So 35 and 15, one of their factors they shared was 5. So that's going to give us a square root of 7 over 3. And that's as simplified as it gets. Woohoo! Done. Yay! So this method was simplifying the fraction. So simplifying it as a whole, all in one radical as a fraction. This method would have worked if they were both like perfect squares. If it was the square root of 36 over 16, then I could have gotten 6 over 4 and then simplified that fraction to 3 halves. I guess I'll draw that example. So another example with this bonus one would be 36 over 16. You could simplify it as a fraction. That would totally work. But if I see it as perfect squares, I'm going to simplify it as 6 over 4, and then I will do the 3 over 2 to get the bonus final fraction. Okay, so knowing your perfect squares is helpful. And then this example 2b, example 2b, we are going to find x. This one's a longer example because it's actually going to apply for our last set of notes in this unit. Okay. So what if we have all of these operations? We have some division, we have addition or subtraction, because that is a legit symbol, plus or minus. We have some multiplication with negatives, we have a square root, we have some squares, we have subtraction under that radical. What are we going to do? So I'm going to show you in order of what steps that we're going to be doing. So I'm going to multiply the negative and the negative 3. So that's going to give me a positive 3. Think about that. Why is it a positive 3? I'm going to keep the plus or minus. I'm also going to keep the radical, and then I'm going to divide by 4. So notice that 2 by 2, 2 times 2 gives us the 4. Now for the radical, there are two terms being subtracted. I have negative 3 squared as my first term. I have a negative 4 times 2 times negative 5 as my second term that's being combined with that negative 3 squared. So I need to simplify both of these terms. Negative 3 squared is a positive 9. Negative 4 times 2 is a negative 8. Multiplied by negative 5 is a positive 40. So notice there are two terms, and this was a negative 3 multiplied by a negative 3 to make a positive 9. Pause the video, make sure this makes sense for this step. All right, now that we have that, we can keep that plus or minus. We just combine everything in the radical, and this plus or minus gives us two options once we simplify this further. So what is the square root of 49? 7. Yes, because you know your perfect squares. Awesome. So I'm now going to split this up. We have one where x is going to equal to 3 plus, that's a 7, divided by 4. And another option where x is going to equal 3 minus 7 divided by 4. So that plus or minus allows us to joint work until we have to split it at the end versus writing out this work twice because it's the same for both plus and for the minus until this last step. So 3 plus 7 makes 10 divided by 4, which then simplifies to 5 halves. 3 minus 7 is a negative 4 over 4, which simplifies to negative 1. So my final answers would be 5 halves and -1. Notice because there are multiple x values, I wrote them with a comma when I boxed them, and this is actually a precursor to the quadratic formula, which you'll see in several videos. So I know I totally went over the 10 to 15 minutes, but we are just under 20/on 20, so I'm going to minimize this. I guess not minimize. I'll go back to PowerPoint. There we go. Comprehension questions, pause it, woo! And you're good to go. Thank you for watching and have a great day.